Right, guys, we've had a look and we've covered arithmetic sequences, we've covered geometric sequences, we've also had a look at arithmetic series. And you'll remember that the difference between a sequence and a series is that a sequence simply just lists the numbers in the pattern, whereas a series actually adds up the terms in the pattern. All right. So we had a look through and we've done some exercises on arithmetic series where we're adding terms of an arithmetic sequence. And we've got the formula for that. And today we're going to move on and we're now going to have a look at geometric series. So I'm going to present my screen again. And again, please just switch your mic on and ask questions as we go. Right. Here we go. Right, so we're looking at geometric series, and that is, as you can guess, the sum of terms in a geometric sequence. So let's just very quickly go through a geometric sequence. We've had a look at the idea that the geometric sequence doesn't obey the first and second differences as we've seen it in the past. Okay, so arithmetic sequences were the linear patterns that we looked at last year, where our first difference was common. Okay, we also had a look at quadratic, where the second difference was common or constant. And if we just keep going on with this pattern, okay, we'll notice that there's no constant difference that actually occurs. So your geometric sequence is not defined by a constant difference. Okay, nevertheless, there is still a relationship, there's still a pattern that exists between the terms. And if we have a look at these terms very carefully, we'll notice that each term is being multiplied by 3 to get the next term. So although we don't have a constant difference, we do have a constant number that we are multiplying by. Okay. And that's what gives us a geometric sequence. So a geometric sequence is a sequence where each term is generated by multiplying by the same number each time. Okay, and we use the letter R to actually indicate that value that we're multiplying by. And we use the letter R because it's called a constant ratio. Now, very important that R does not have to be a positive whole number. That R could be a negative number. That R could even be a fraction. There are some limitations on R though. R cannot be 1 and R cannot be 0. Okay, so if we have a look at that sequence, then our geometric sequence takes on that type of pattern. So term 2 is term 1 times our constant ratio. Term 3 is term 2 multiplied by the constant ratio, etc., etc., etc. Right, so if we take an example, hopefully if you look at this example, you can see here that each term gets multiplied by 2 in order to generate the next term. All right, so we have kind of a general term there. Yes. Somebody have a question? Sorry, I just had a little ping on my microphone.
So I just was gonna say, so R can be a fraction.
Yes, R can be a fraction, and it can be a fraction that's bigger than 1 or smaller than 1. So if it's smaller than 1, we have the case where the terms actually become smaller themselves. Yes. And I'm talking about smaller as, so if we got 16 and my common ratio is a half, then we're going to go kind of almost backwards from this. So first term will be 16, then 8, then 4, then 2, then 1, then a half. Okay, and we're going to have a look at those sequences. We're going to have a look at that particular sequence or series in a lot more detail next week, because there's some special properties about that. Okay, and hopefully as we go through today as well, you'll kind of pick up something interesting that happens with geometric series. Right. So each term is multiplied by 2 in this case. And you'll see that this formula that we've got over here actually presents a problem because it relies on knowing the term before. Okay, so if we now look at what these things actually look like. So what I've done is I've taken the term positions, so the values for n, and I've compared it, I've plotted it against the actual values of the term itself. So I've plotted n against Tn. Okay. So if we're going to take the first sequence that we started with, and that's where we're multiplying by 3 each time, when the value of n is 1, Tn is 3. Second term is 9, third term is 27, fourth term, etc., etc., etc. If we plot that graphically now, that's what our graph actually looks like. Okay. And what does that look, what type of graph does that look like? If we had to join those points, sorry?
Wouldn't it be an exponential graph?
It looks very much like an exponential graph, doesn't it? Okay. So if we had to join those points, and we can't join the points because we don't have all these other little values in between the whole numbers, but if we had to join those points with a dotted line, it would very much look like it's an exponential graph. So our geometric sequences or series are then exponential, right? Which means my general term for them must be something that looks exponential. So these are just a couple of properties that we've discussed when we did geometric sequences last term. Again, my first term is represented by the letter A. We're multiplying by something the exact same amount each time, and that's called our common ratio. And the common ratio is denoted or represented by the letter R. And sorry, that should be n minus 1 up there. Okay. My general term is a to the r, ar to the n minus 1. In other words, I'm multiplying by 1 less r than the number of terms that I've got, which makes sense because if I take term 1 is a. Term 2 would be a times r. Term 3 would be a times r to the n. So I just want to change this here so that we don't get it wrong. Okay, so this exponent here is always 1 less than the position. We found that with arithmetic sequences as well, where the d value was being multiplied by always 1 less than the actual position. Okay, this formula over here, r is equal to Tn over Tn minus 1. That is how we can actually work out our common ratio. So if we've got consecutive terms, we simply divide the consecutive terms, and that tells me what my R value is. This one is for non-consecutive terms. So I divide the two non-consecutive terms. This K value over here is the number of terms between the two terms that we have. So if I've got T7 and I've got T11, then K would be 4. And then I would divide T11 by T7, and that would give me R to the power of 4. We've done all of this last term, so this is just to get these things back into your head before we actually have a look at series and how we add these terms together. Right, so those are just properties about a geometric sequence, okay? And now let's have a look at geometric series. So I didn't want to go through the whole confusing exercise of you guys trying to find this formula again. I do have a task that you can do if you're interested, and you can just let me know and I'll forward it to you. Okay, but here's the equation that we have for a geometric series. All right, so the sum to n terms is the first term, a, multiplied by r to the power of n, in other words, how many terms we're adding, minus 1, all over just r minus 1. And we can write that the other way around as well. It's really up to you, whichever way you choose. I switch between the two. If my r value is bigger than 1, then I use this one. If my r value is a fraction smaller than 1, then I use this one here. Okay. It's just an easy way to be able to make sure that my numbers all work out nicely. But again, you're going to be putting it into your calculator, and so it's not really that important which one you use. Okay. Right. So there are, as I said, some restrictions there. R can't be 0 and R can't be 1 either. Okay, so example 1. Let's have a look at how we're going to use this in an example. So in that series, 1 plus 2 plus 4 plus 8, and we've seen that already this morning, that particular sequence. Right, they've asked us, or I've asked you to calculate S17, which means I want you to find the sum of the first 17 terms. Okay, so how do we do that? Well, we just go back and apply this formula. Okay, my A value will be 2, my N value will be 17, my R value, okay, sorry, my A value will be 1, my R value is 2 because I'm multiplying by 2 each time. Okay, so the solution here is going to be A, which is 1, okay, multiplied by 2 to the power of 17 minus 1 all over 2 minus 1. You just put that into your calculator, and I'm hoping that you're doing that with me right now to be able to get the answer of 131,071. So if we add those 17 terms together, we get 131,071. Was there anybody who didn't get that answer or don't understand how I'm getting that answer? Okay, great. Let's move on to example 2 then. Okay, how many terms of that series will add up to that? So in this example, it's now wanting us to work out the n value. So my Sn is equal to this horrible looking fraction over there, okay? So our Sn is equal to that horrible fraction over there. My A value is 1026. And here we can see we have a case where my second term is now smaller than my first term. Okay. Which now means that my ratio, my constant ratio, is now going to be a fraction between 0 and 1. Okay. So remember, to work out R, we divide two consecutive terms. So we're going to take 342 and we're going to divide it by 1026. Okay, so 342 divided by 1026, we get 1/3 as our constant ratio. Right, so we actually end up with an exponential equation here. Okay, and I actually want to do this working out, so I'm going to just set up my computer and my phone again over my board, and we can then do this one together. Okay.
Sir,
Yes.
I just wanted to ask, are we going to be like given all of the formulas? Because there's a lot within all the different like series and then the sequences. Or do we just have to know all of them?
No, the formulae will be given to you. What I'll do later is I'll actually post the formula sheet for you so that you can see which formulae are given to you on the formula sheet. Okay.
Okay, thank you so much, sir.
Pleasure. Okay, guys. Sorry. Okay, are you able to see my whiteboard? Whoa. Okay, are you able to see the whiteboard?
No, sir.
Okay, you might need to pin my other person, pin my other entry, and then come back to my presentation just now.
Yeah, it's in now, sir.
Okay, so the question we were given, we had this horrible fraction. Let me just get back to the question. So far we know that R is 1/3. Okay, we calculated that by taking 342 and dividing it by 1026. Okay, we also know SN 41534 over 27. Okay. We also know my formula. My formula is A R to the n minus 1 over R minus 1. And this has got to give me that nasty number. If I now substitute, I get 1026, a third to the n minus 1 over a third minus 1. And we still equal to this horrible number, 41,534 over 27. Okay, if we simplify this, now this is why I use, or I'll go between both of them, because I'm now able to simply just turn this equation around, or to not the equation, but I can turn these two numbers around in the fraction, as long as I turn those ones around as well. And the reason I do that is now I actually don't have to worry about a negative. Okay. This here simplifies down to 2/3. I can get rid of this 2/3 by multiplying both sides by 2/3. Okay, so if I multiply that 41,000 number, okay, we now end up with our 1026, 1 minus 1/3 to the n is equal to an even more horrible looking number, 83,068 over 81. Right, now what I'm going to do is I'm going to leave this bracket here until just now. I'm going to divide by the 1026, the 1026. And when I'm dividing, hopefully we can still remember that that's the same as multiplying by 1 over. Okay. Right, so if we take that answer and we multiply it by 1 over 1026, it looks slightly better. And we've got 1 minus 1/3 to the n. Okay, obviously I don't need the brackets there anymore because there's nothing else associated with it. And that is equal to 2,186 over 2,187. Right, if I subtract 1 now, I want to get rid of this 1. So I'll move it across and it becomes minus 1 on that side. We end up having negative 1/3 to the n is equal to negative 1 over 2,187. Our negatives now can both cancel out, so that's quite a good thing. And now the trick is to be able to find what is 2,187 as a power of 3. But fortunately for us, we don't need to worry about that because we can simply just change this into log form. So we get log base 1/3 of 1 over 2,187. And whatever answer I get there must be the answer to n. So log base 1/3 of 1 over 2,187. And we get an answer there of 7. Any questions about that, guys? Anything that you want me to go through a little bit slowly or go through again?
So how do you know to use your logarithm?
Nix, because I'm working with an exponential equation, I'm wanting to find the exponent. So the only way that we know how to, well, there's 2 ways we know now. The one way is to get this thing as a base 1/3. So if I can just do an easier one on the side here, if we had 2 to the n equals 8, In the past, we could have taken that 2 to the n and made it equal to 2 cubed, and then just said n equals 3. Okay. Some of you could be a lot brighter than what I am and know that 2187 is 3 to the power of 7. I didn't know that. So I needed to then use logs, because it was a far easier method than for me trying to work out what 2187 was as a power of 3. Any other questions, guys? Okay, let's go back to our presentation. Okay. There's example 3, right? I'd like you guys to try that one on your own for a little bit. Yeah, guys, I'm sorry about this example 3. This example 3 is actually arithmetic. Okay, so don't worry about that example 3. Okay, are there any questions about geometric series, guys? Okay, I think you would have seen that the work I set was exercise 1.6, number 1. That is an exercise simply just adding the terms. Okay, I want you to get practice at that first, and then we'll have a look at some further examples tomorrow, and you can carry on with other questions from that exercise.
So this PowerPoint isn't on the classroom yet, is it?
I thought I did put it on this morning. No, it appears I haven't yet, Nicole. I will post that immediately.
Thank you so much, sir.
Okay, I've saved it after making those corrections. And then I'll put it up right now. Obviously, the solutions that I've done on the board aren't there. Okay. So hopefully you guys were taking those down as we were going. The first one was fairly straightforward. The second one we did together. Cheers, guys. Look forward to seeing you again tomorrow.